Let's say you're given this situation here where we have a yo-yo at rest and then we let it go and it travels a distance of h, spinning on its axis, and the question wants you to calculate the speed of the yo-yo. First thing to note is that in this situation, we have both rotational and translational motion. And so in this type of motion, the total kinetic energy is actually 1.5 times more than just translational motion. We can note that the rotational motion adds half times more kinetic energy to the total kinetic energy. Noting this, we can start off by using the conservation of energy, which states that the energy before is equal to energy after. At the start of the motion, the object's at rest, so we don't have any kinetic energy, so it's just potential energy before. And then after, we have the kinetic energy from rotational, kinetic energy from translational, and we have the potential energy after. But looking at the diagram above, we can see that height's going to be equal to 0, and so the potential energy after is going to be equal to 0. Here we can plug in our general definitions for the gravitational potential energy, the rotational kinetic energy, and the translational kinetic energy. If we do that, we get this expression here. But what is I, which is the inertia for the rotational kinetic energy term? For a circle, the inertia is equal to 1/2 mr squared. Also, what is omega for this motion? We can also replace omega with VCM over r. This relationship holds when they assume that there's no slipping in the motion. And so if we do that, we get this expression here. Start by bringing the square to the bracket in this term, and then we can cancel out the r squareds, and then we can further simplify and add these two terms together to get this expression here. And then we can isolate for the VCM, which is the velocity of the center of mass, and we get this for the final answer. Note that this makes sense because this is the rotational kinetic energy term, this is the translational kinetic energy term. From the start, we noted that the kinetic energy with rotational and translational is 1.5 times. And so look at these two terms here. The rotational is 1/2 the translational. We see that the total kinetic energy is actually 3/2 the translational, which makes sense